Okay, good morning, everyone. A very happy new year to each and every one of you all. Hope you all had a good week, the previous week gone by. I was unavailable since I had gone out of town, but I'm back and we will continue from where we left off with regard to sensors. Okay, the remaining topics of sensors are level sensors and your fire detection sensors. Okay, so if not in the next 2 days, by another 3 days, we'll be finishing off this particular topic. So I hope all of you all can hear me clearly and can see the screen also clearly.
Yes, sir. Happy New Year.
Yes, sir. Okay, thank you so much. I see very few people have joined. Perhaps it's a carryover of New Year's Day. Anyway, so let's start level sensors. Okay, now at this stage, let me tell you, when we are talking about level sensors over here, it is with regard to level in a cargo tank. So we are talking about mostly levels in your gas tankers, your chemical tankers, your oil tankers. Okay, we are not talking about levels, say, in your bilge tank, your levels in your, service and other tanks. Yes, you can even have it in your bunker tanks, but we are not talking about service tanks and all that, where you have other more cruder methods, which are more than enough for that purpose. Okay, so also you have the water ingress system. No, we are not talking about the level in that system, because your water in bilges, your water in that water ingress system, they are only indicative of water being where it should not be. Okay, your bilge, yes, it has water, but it will not give you an alarm till the water in that bilge reaches a certain level. So in those instances, it is only high and low level, high level being the alarm that is indicative that yes, maybe some water, some pipe is leaking or some thing is leaking, and that is why that bilge has filled up. Or in the case of your water ingress system, normally there isn't any water, say for example in your forecastle, and then suddenly water comes there for whatever reason. Maybe they have left that forward hatch open after stations, and you'll have gone into rough weather and water has all got into the forecastle. So that is only an indication that water has got into a place where it should not have any water. Okay, but here we are talking about level sensors of tanks that are going to be carrying liquefied cargo. Okay, so once again, let me also remind you that at the start of the sensor topic, I had mentioned that certain sensors are not practical for use on board, certain sensors are obsolete, etc., etc. Okay, so in these level sensors, and one of those sensors is this level sensor by means of capacitance. Okay, it is not practical for practical for use on board ship. The reason will become very, very apparent. Okay, and we'll also see a video where that person very categorically states, if one needs to change whatever the liquid is in that particular tank, then you have to recalibrate that sensor. So that is why this type of sensor becomes not practical for use. Okay, so we will see how that becomes a non-practical sensor for use on board ship. But since questions are asked on how do you measure level by means of capacitance, we need to know this. Okay, so the all important formula, everybody knows C is equal to epsilon multiplied by A divided by D. Okay, C is your dielectric strength. Okay, this is the area of the plates of a capacitor, and of course this is the distance between the plates of the capacitor. Okay, as we know, your capacitor has two plates. Okay, now in a sensor or in a capacitor, once it is made, the area remains the same, the distance remains the same. Okay, and the dielectric remains the same. This is, I'm talking about a normal capacitor. But where you have a capacitor that the capacitance can either increase or decrease, then any of these parameters, if it changes, you will either have an increase or decrease in the capacitance value. Okay, so if you're having an area that is going to increase, then obviously your capacitance is going to increase. If the dielectric strength increases, your capacitance is going to increase. If your distance between the two plates increases, then your capacitance is going to decrease. So this capacitance, change in capacitance, is sent into an electronic circuit that will be changing this capacitance into a level. Okay, let that level be inches, feet, meters, whatever. This capacitance is sent to an electronic circuit, which converts the capacitance change into a level. So there is a direct relationship between the capacitance and the level in a particular tank. Okay, so let's see how this particular thing works. Okay. So here's a particular sensor using the capacitance type. It is put into a tank. Okay, so here's your tank, and assuming there is nothing in the tank, when there is nothing in the tank, what are you going to have there? You're going to have air as the dielectric, and the dielectric strength of air is, everybody knows, is 1. So whatever you're going to fill into this tank, from water to oil to whatever the substance may be, depending on what the substance is, that substance will be something greater than 1. Water will have its own dielectric strength. Your certain crude oils, you have various grades of crude oils. Okay, you go to even Rastunora, those who have been on tankers will know, you have various grades. Some grades are so thin that you think that it is actually diesel oil, whereas it is actually this thing, they are called distillates. Okay, so it is so thin that you think it is diesel oil. Okay, so that will be having another dielectric strength. Your normal crude oil whatever the crude oil might be, will be having a certain strength. You go from Saudi Arabia to another port and load their cargo, then that also will be having a different thing. So that is why I said this particular system on board the ship, due to the various epsilons, okay, this is the epsilon that keeps changing. And if you are going to keep changing the epsilon, the dielectric strength, the various grades of fuel, then obviously whatever this thing, you're having all the electronics in this unit, which, as I said, you're going to change the capacitance into a level. So this is going to be changing it into that particular level. So every time you're going to load a different cargo, this is going to be changing. Okay, the epsilon is going to be changing. So you will have to every time recalibrate or even sometimes change some components, which therefore makes it not practical for use on board ship. Okay, but since, as I said, it is asked the basic principle of working, let us see how this goes about doing its work. Okay, we said we require 2 plates of a capacitor and the dielectric. Okay, so this actual sensing element that you can see here in black, the inner plate of the capacitor, that is forming 1 plate of the capacitor. Okay, where is the other plate? Generally, it is taken as the outermost part of your tank, but then if you're going to have the outermost part of the tank, that means you're going to have an electrical connection over there. Now, as you know, we are working in a hazardous region. Yes, you can have intrinsically safe, this, that, everything, but they try to avoid that. And therefore, instead of having the outer part of your tank as the second wall of your capacitor or second plate of your capacitor, this tube within which you are having the main sensing element as 1 plate of the capacitor, this tube is taken as the second plate of the capacitor. Okay, so you're having 2 plates of the capacitor. Now, what are you going to have? Initially, whenever the particular tank is empty, you're going to have air, as I said, and everybody knows air epsilon is equal to 1, the dielectric strength is equal to 1. Now you start filling up the particular liquid into that tank. The chief officer starts filling up that liquid into the tank, whatever the liquid is. Okay, this is a hollow tube, mind you. So whatever liquid is filled into the tank will also come within this tube and start rising. As it comes within this tube, what are you going to be having? You are going to have your particular dielectric strength changing. Okay, so say the liquid has come there. This much the dielectric strength has changed. As the liquid rises, it keeps changing, keeps changing, keeps changing. Okay, as you can see, suppose the liquid is here, the dielectric strength has changed over here compared to this. This one is still epsilon 1. Okay, air is equal to 1. Here still air is there, but here, whatever the liquid is thing, the epsilon has changed. So that particular thing is sent into your electronics unit. Remember, C is equal to epsilon multiplied by A divided by D. Since epsilon is rising, your capacitance is also going to rise. That means the level is rising. So there's a direct relationship with the change of your capacitance and your level. So whatever is going over here is changed from a capacitance reading into a level reading and calibrated such that it gives you in feet, inches, meters, whatever the particular thing is. Okay, so this is how your capacitance level indicator works. Okay, everybody clear? Right, so let's see a short video on this. Okay, the video shows right from the basics of the capacitor. So I won't be going through that. When I post the video on the group, you can see the entire video. Okay, so they are just talking about the capacitor over here. And let's see where it actually works as a A level sensor.
As a dielectric liquid is introduced between the electrodes of the capacitance changes progressively and liquid level can be determined. To measure variations in capacitance, electric energy flowing into and out of the electrodes is measured as the circuit potential is varied. A regular flow of energy is established by connecting the electrodes to an alternating current measurement circuit. The more energy flow to the electrodes, the greater the capacitance, meaning more dielectric between the electrodes. For sensor calibration, reference measurements at empty and full tank conditions must be taken. Generally, we need to know the dielectric constant of the liquid being measured to calibrate the sensor at its full condition. With the empty and full outputs established, liquid level sensing comes down to relating sensor output to these values. Capacitor plates can also be deployed as concentric tubes, with the advantage of reduced interference, as well as improvements in mechanical stiffness and robustness. Fully integrated electronics mean no external electronic units are required, as all signal processing is managed on board. Dielectric fluctuation caused by temperature variation is managed using offset values also stored within the sensor memory. These values are typically applied during factory calibration at GIL sensors. A wide range of fluids can be measured using a GIL liquid level sensor, including fuels, biofuels, diesel, and oil, and by modifying internal components, the liquid level of electrically conductive substances, such as water, can be measured. Sensors are often constructed from aluminium, stainless steel, carbon fiber, or PEEK, or a combination thereof. This allows GIL to cater for applications from fuel tanks in Formula One race cars to oil transmission systems in mining and industrial machinery.
Okay, so you would have seen and heard in that video that yes, your particular level within a tank can be measured depending on what that liquid is. And they said that if you're going to change that liquid, you will have to recalibrate this. So as I said, on board the ship, this is not a practical solution, because every time you're going to load a different grade, then you will have to recalibrate this electronics unit. And even as they said also, you might have to change some components. So therefore, not a practical measuring device of level on board ship. Where would you have such a particular thing? Yes, if your ship is going to carry that same cargo throughout its life, okay, say maybe one of these small tankers you find very often in the Far East, they might be carrying the same cargo again and again and again and again, then yes, maybe those type of ships will have. But otherwise, this type of sensor is limited to show use. As you heard in the video, you're going to be having it in cars. Even the video also showed one gauge that looked very typical of your fuel gauge in your car. Okay, so you are loading that same fuel again and again. You're not changing from diesel to petrol or to something else. Okay, so you're going to be, if your car is petrol, is going to load only that particular petrol, and the specific gravity and the components and whatever that goes into that making of that petrol from the refinery, that thing is going to be the same each time. Also in your petrol pumps, whenever they're going to be loading into their tank, they are going to be loading only petrol in one particular tank and your diesel in another tank. They're not going to be interchanging every time, because then those petrol or diesel dispensers will have to be recalibrated every time. Okay, so it's as simple as that. Okay, so this was your capacitance level sensor. Okay, any queries or doubts? Okay, so the next type of level sensor, this is still there on some ships. Mostly, if you have Korean or Chinese built ships, then they are using it for your bunker tanks. Okay, there is one huge drawback, very simple principle of working, but there is a huge drawback in this type of system. Okay, and this is your air bubbler level sensor. Now, as you can see over here, this air bubbler system, you are getting your service pressure, 7 bar service pressure from your engine room. And through a regulator, you are regulating that particular air to come through this T-section tube. It's a hollow tube. To the other end of the top part of your T-section, you are having a level transmitter. Okay, it's a local gauge that is going to be changing this particular level into a 4 to 20 milliamps that can be then sent to a remote position for its readout. For example, maybe this might be a cargo tank or a bunker tank, and the chief engineer, yes, he might be in the CCR usually, and you generally have in your cargo control room, you have these particular gauges over there, no, for your bunker tanks. So that is why he's sitting over there and watching those things. So yes, so that signal from a local thing will be sent to that thing in the CCR so that he can read out that particular level within that tank. The longer part of the T goes into the tank. So it's a hollow tube, as you can see. So when there is nothing in the tank is empty, then whatever air that is sent and reduced such that or adjusted such that air is going to come out here at the bottom end of this tube when the tank is empty. Okay. But as the tank starts getting filled, okay, you are getting your tank filled up slowly. And then when the tank level comes and just about seals the tube, obviously, you're going to get a back pressure acting in this manner. Okay, the back pressure is going to be acting up in this particular tube and of course going towards this particular pressure gauge or pressure transmitter. So you can see as the level is going to increase from this particular thing, whatever is the back pressure over here, and if you're going to compare when the level has reached over here, the amount of back pressure that is created from this level to this level, obviously at this level, the back pressure that is going to be acting on this particular level gauge is going to be much more than when it had first blocked this tube. The regulator over here will regulate the air such that you will still get some air bubbles coming out from the bottom. It's not totally blocked off. Okay, very minute amount of air bubbles will be allowed to still come into the tank. Okay, everything is calibrated, so to speak. This regulator is calibrated, so also this gauge is calibrated. And as the level within the tank increases, so also the back pressure within the tank also will increase. So the back pressure that is acting onto this particular level gauge, okay, is directly proportional to the level within the tank. So whatever the back pressure, this particular gauge is calibrated to give you whatever the reading, let it be in feet, let it be in inches, let it be in meters. Okay, and of course from here it is going as a 4 to 20 milliamp signal to a remote indicator where you can read out that particular level within the tank. Now, why did I say that this thing has a very big drawback? Okay, earlier they used to use it in ballast tanks, And very often I used to get a call from the chief officer, Bhatti Sahab, ye kaam nahi kar raha hai. I am filling my tank. I'm still, this thing is showing you between 0 and something. It's not increasing. Whilst it was just being filled up, I was getting a reading, but abhi band ho gaya. Now, what can be the reason? This is a metal tube. Okay, it is a must. Let's say this is a ballast tank. Okay, so if there is a hole over here, right, up till this thing, you're going to get something, but because there is a hole here, some of the air will escape out from here, isn't it? Instead of the air escaping out over here, some of the air is going to be escaping out here. So when it is going to be filled past this hole, air is leaking out here, air is leaking out over here. So what is going to be the back pressure? The back pressure is going to be much less than what it would have been if this hole was non-existent. Okay, so that's why the chief officer would have said, abhi tak mila hai, but after that it's not increasing. It's because a hole has been formed at some point in the thing. Not one hole, sometimes you get several holes. Okay, so this is what is the biggest drawback. Let it be a bunker. And now they've totally done away with it in the bunker tank, in your ballast tanks. But still, as I said, on your Chinese and some Korean vessels, you will still find these in bunker tanks, and invariably you're having a problem in this particular thing. The chief engineer doesn't depend on this, because he'll be having his engineer and oiler, duty oiler, always checking the levels by means of that tape. Okay, so basically this also is being phased out, though not completely phased out. Okay, so this is how your air bubbler level sensor works. Any queries or doubts? We'll see a short video on this. It's an animated video, so let's see a video on this one also.
Bubbler level measurement working principle. A fixed constant air supply will be given at the inlet. When there is no level in the tank, then total air passed to atmosphere through pipe in the tank. When the level in tank increases means the proportional back pressure increases, and the increased back pressure is proportional to level in tank. When tank level is more, then back pressure will increases. With the use of electronic transmitters, like pressure transmitters, we can convert the back pressure signal into 420 mA level signal.
Okay, any queries or doubts on these last two level sensors? As I said, the capacitance one is generally not used on board. In fact, it is not used at all unless it is that particular vessel is designated to carry only one particular cargo every single time of its lifespan. Okay. Otherwise, it is not used on a normal cargo vessels. Okay. When I say cargo vessels, I'm talking about oil, gas, and chemical tankers. Okay. Air bubbler system is also being phased out for the simple reason that it is not a very, very reliable system due to the holes that can be formed in the pipe that goes down into the tank. Okay, so now the next system, and this system is still very much in use, although not a very accurate system. This system is still used on board, the float magnet resistance type of level sensor. Okay, so let me magnify that. Okay, I think it's big enough. Right, so here's your cargo tank. Let it be a oil tanker, gas tanker, whatever tanker. Okay, you're having your particular sensor, the same thing that is going to be going down. Okay, here is a hollow tube, excepting you're not going to have that sensor element that we saw in the capacitance type of level sensor. Instead, what are you going to have in around this hollow tube is a particular float. Sorry, I've got to change my pen. Okay, is a float. Okay, so a float is going to be there. I'm only showing part of it so that I don't, I might as well color it. Okay, so this is your float which is there. Your float is basically a donut shaped element. Okay, so the particular pipe will be going right through, and as the level increases, this float is going to move through this hole up this particular pipe. Okay. Now within this float, and here you have a cutaway section of that particular donut shaped float. Inside this float, you are having a permanent magnet that is colored blue. Because this is a cutaway section, you're seeing it on both sides. Otherwise, it is exactly in the same manner as this float. It is a round shaped magnet. Okay. Now, as the level goes up, so also will this float, so also with the magnet within that float. And as it is going past inside this particular element, inside this particular tube, you are having an element that is carrying several groups of resistors. I've shown only one resistor each over here, but each of these resistors is representing a group of resistors. Okay? Across each group of resistors, like I've taken this one as an example, across each group of resistors, say 1, 2, 3, and 4 resistors, you are having a particular reed switch. A reed switch looks something similar to this. Okay. You are having magnetic contacts. When I say magnetic, they are not magnetized. They are general metal strips. Okay. And when a magnet passes, now each of these metal strips will be having north and south poles, tiny, tiny north and south poles. Each one will be arranged in a different manner. Okay, north and south, south and north, north and south. Okay. If you remember, somewhere else I had mentioned, they are all hera-fairy when we were talking about the hysteresis loop. Okay, so they are all mixed up and therefore they are not magnetized. And when they are not magnetized, these two things are not going to be touching each other. In other words, this is acting like a switch. So when they are not magnetized, this switch, which is the reed switch, is in the open condition. Okay, now as this float moves past each of these groups of resistors, what happens is just like as we had in that hysteresis curve, all these tiny, tiny magnets get arranged in a proper manner, and then these get magnetized. And that's the time when this particular reed switch contact makes. So the reed switch inside actually gets closed. So now it gets closed. As the float is moving in the upward thing, it has come across this resistor. It has come across that particular reed switch of this group of resistor, and it has closed that particular reed switch. It goes up as the level goes up. That resistor group of resistors is encountered together with its own reed switch, and then that reed switch gets closed, and so on and so forth. It goes up and up and up, and finally comes to the top level of the tank. So as each group of resistors is shorted out by the reed switch, you will be getting an indication in the cargo control room as each particular thing is going to be shorted out. The reed switch getting closed in each instance. Okay. And then when it finally reaches over here, then you will be getting your particular maximum this thing, and normally nobody fills it 100%. Okay, so finally your second last LED will be lit. Okay, so this is the way that this type of system works. And when you are going to, or when the chief officer is going to discharge his vessel, obviously the float, which is now somewhere here, that float level is going to drop. Okay, and when it drops, it's going to come in the opposite direction to when it was traveling upwards. So when it is going to come in the opposite direction, it is once again going to make all these tiny magnets within these two strips once again into this method, Hera-Fairy method, and it is going to demagnetize these contacts. When it demagnetizes the contacts, you are going to open the respective switches, reed switches, as your level begins to fall. And then one by one, your particular segments over here will be extinguished, okay, till you come to the bottommost this thing. Okay, and generally you're going to be having unpumpables, which will be probably indicated by this last red LED over there. Okay, so this is how your float magnet resistance type of sensor works. Any queries or doubts on this? Okay, so it is still used on board the ship. In fact, one of my companies that I worked for, K-Line, they had all these type of float magnet resistance type of level sensors installed on their ships. Now, if the Japanese are going to use it, even though not 100% accurate, yes. Why? When we are not really interested. We know that, you know, the levels are going to go up. Okay, the drawback is, and I've deliberately shown by a big gap over here, the gap is not so big, but just to indicate that between this group of resistors and this group of resistors, you are going to have a small break. So you are not going to get, say, from 1 meter, it's not going to go to 1.01 or 1.02 and so on and so forth. It will go from 1 to 1.1, then might be next one will be 1.2, then 1.3, and so on and so forth. Okay, so it's not going to be a very accurate readout like this. Okay, so that is because of this gap between these groups of resistor. So this is one drawback, and therefore whenever the chief officer is topping up, okay, he will not be depending on this type of thing. He will be with his deck crew on board, taking the allergics in order to get the correct thing. So, so as to not create a oil spill or anything of that sort. Okay. Everybody clear? Any queries or doubts on how this type of system works? Right. So, excuse me. Just give me a moment. Right. Finally, we come to what nowadays we are having on most tankers. Excuse me. And that is your tank radar system. This is a highly accurate thing whereby you will get at any given instant what is the level within the tank. Okay, so let's see this particular, let me zoom out a wee bit. Right. So we'll see this block diagram and check out what each and every block is over here. Right. So let's start with the leftmost part of the block diagram. This dome shaped thing, okay, I made it roundish. You can have it roundish, you can have it square. Okay. So it can look like this, or it can look like this. Doesn't really matter. They are one and the same thing. Okay, so looking at that particular thing, okay, this is called a TGU, very big name. tank gauging unit. Okay. And what is this tank gauging unit? It is this particular thing that I mentioned. Okay, this outer covering where you can see the bolts. Of course, here there's your clamp-like structure which is holding in. This particular covering, which is a waterproof covering, that is called as the TGU, tank gauging unit. It is just a waterproof enclosure. That's all. Okay. Within this particular TGU, you have the TGE. And what is TGE? TGE is nothing but the tank gauging electronics PCB. Okay. Now, the tank gauging electronics PCB, let's see where it's somewhere down here. We'll see how it looks or what it's more or less looks like. Okay, so you can see this is on a tanker. You can see this. Mr. Nitin Mishra, kindly mute your microphone.
Sorry, sir.
Thank you. No worries, as long as you realize it. Okay, so this is how it looks on a tanker. And let's see what is inside that. And here's a particular, let me zoom out a wee bit. Okay, so this is your TGE. The electronics box over here it is called, or electronics PCB. There is all the electronics in over here. The electronics over here is going to convert whatever signal that comes into a radar signal. And when the radar signal comes back as an echo, then it is converting it into an electronic signal that is then going to be sent to another part of that particular system. Okay, so this is your TGE, which over here is located over there. Tank gauging electronics board or PCB. Okay, you can also see I've colored here something in blue, and that something in blue is nothing but your sensor for your IG pressure. Okay, it's an IG pressure sensor which you can see over here. Your temperature sensor is not included in this. Your temperature sensor is in fact located outside, but all the wiring comes into this particular TGU. Let's see that in a previous photograph. Right? So here your particular TGU, inside which is the TGE as well as your IG pressure sensor. But outside you are having the temperature sensors, as you can see here. And then the wiring and all that is then going into this particular unit or this particular unit and into the TGE. And from the TGE, you're going to get it at a remote display. Okay. So your temperature sensors are separated from your IG sensors. Okay. So as I've shown here, this is your temperature sensor and here's your IG pressure sensor. Okay. Of course, you are going to be having your dish antenna, as you saw. Okay, the radar signal is going to be bounced off the dish antenna down into the tank, and of course the returning echo is going to come, hit against the dish antenna, and then be taken up by that receptor called the Allen beam. Okay, so very same as what you're having in your direct to home television. Okay, very same thing. So this is your particular thing within the tank and just outside the tank. Okay. From here, the signal that is sent by the TGE is going into another unit called the SCU or level unit. SCU standing for Signal Control and Communications Unit. Okay. This is the heart of the entire system. Okay, it is the brains of the system, if you want to call that. So where is that over here? This is your level unit or SCU. Let's see how further it looks like when it is opened. Generally, it is on your A deck, in the deck just below your CCR, or it is located in the CCR itself. Okay, so let's have a look. And this is your particular SCU or level unit. The topmost section consists of the computerized part. Okay, within that particular thing, you are going to have your backup display where you can set your particular levels, high, low level, whatever you want. Okay, so this is one backup display. We'll be seeing another backup display which can be located either in the captain's cabin or on the bridge if it is so required. Otherwise, the main backup display is this one that is located within the SC. Over here, you are having several of those ports. Now, what are these ports? These ports are the connections that are coming from all these TGUs. Okay, remember, as I said, from here, or the TGEs, then the TGU, and whatever the wiring that is going, as you can see, the wiring is going into your SCU. Okay, so that is what that particular thing is. Okay. So those are going to be coming in over here. Okay, so this must be a chemical tanker. As you can see, 1, 2, 3, 6, 9, 12, 15. So 15 and 15, 30 tanks. So this must be a chemical tanker, because your chemical tankers have several small tanks. Okay, 15 on the port side, 15 on the starboard side. Okay, if it was a crude oil tanker, then you won't have so many things. Okay, right. So these are the ports to which your TGEs are coming into the particular unit called the SCU. Right here at the bottommost section, you are going to be having your IS barriers, intrinsically safe barriers. Remember, and when we are going to be doing that topic a little later, remember that all these sensors are located in the hazardous region. Anything forward of your accommodation is considered as the hazardous region. Your temperature sensors are going right into the tank. Okay, so all those particular sensors have to be safeguarded against anything that can possibly cause a spark. And if there is a spark, you are inviting trouble in the form of fire and explosion. So your IS barriers over here are going to prevent that. This particular section here is nothing but your power supply. Okay, power supply not only for the SCU, but for the entire system. Okay, so that is what is your SCU, and that is this particular block over here. Then you have an interface. Okay, this interface is between your locator or workstation that the chief officer uses only for his loading and discharging operations. No other, this is a dedicated computer only for cargo operations. No other program is allowed to be loaded onto that computer. Okay, it is a certified computer by the particular flag state, or whoever is the thing that you say, like Nippon, or whoever this thing is that is authorizing those things, they will be certifying that this particular computer is okay for use for cargo work only. Then you have the main and the backup display. Now the main display will look something like this. You can have it in a graphical, the segment type of graph that I had shown you whilst explaining the float magnet resistance type. You can have it either this way, or generally whenever you are having the tank radar system, most of the time the owners or whoever is running that ship, they prefer the screen display as shown in this particular case. Okay, so as I very rightly said, you are going to be having so many tanks, it definitely must be a chemical tanker. Okay, so at any given instant, you can make out immediately the exact level within that tank. If it is changed by 0.01, then yes, it will show 0.01 difference, then 0.2, 0.02, and so on and so forth. So this is a very, very accurate readout. So this will be your main display, or in the graphical form. In the graphical form, you will not be able to decipher very correctly. But yes, this one will give you a very, very accurate readout of the level within the tank. So the other backup display, as I said, could be either on the bridge or in the captain's cabin. That is depending on the owner's requirements. It need not be so. Okay, so you can have only one main display. You don't have any other backup display like this. The only other backup display is, as I said, located within the SCU, Signal Control and Communication Unit. Okay. So that is your tank radar system as far as the block diagram is concerned. And with regards to the working of the system, when they first started, it was SAB that had first started out this particular system. Okay. As you can see, SAB tank radar system. SAB was the first one to discover the system, and whenever they had discovered it, they had all the patents. In other words, nobody else was allowed to use it. And when they started out using it exactly like your nautical radar system. Now, one thing is different between, not one thing, there are one or two things that are different between this system and your nautical radar system. So one of the questions that are asked in the oral is, how does your tank radar system differ from your nautical radar system? Now, I may have confused you by saying when SAB first started out, they started working on the same principle as your nautical radar system. But the main difference between your nautical radar and this radar is very easy for you to know. Here's your particular ship. Okay, your particular accommodation, and on the accommodation, you are having your main mast with your radar. Somewhere in the distance, there is a target. So your radar is transmitting. Okay, I've deliberately drawn dash lines, dots rather. And if you have already done the nautical radar system with Mobin Sir, you know that in this radar, number one, the radar signals, the RF energy that is sent out in pulses. Okay, one pulse, next pulse, third pulse, fourth pulse, etc. Your main radar, nautical radar, is sending out its radar signals in pulses. Why are we having it in pulses? So that when you are getting a returning echo, remember the pulses that are going, echo has to come back. If this is going to go as a continuous radar transmission, the echo that is coming back, normally the echo is how many miles away? It is not like this, okay? This might be only in a few meters. Say even, let's say 40 meters. This can be nautical miles, okay? 1 nautical mile is 1.8 kilometers. Okay, so even if it is 1 nautical mile, that is 1.8 kilometers, this is only 40 meters. 1.8 kilometers is 1,800 meters. Okay, So your returning echo that is going to come even from 1 nautical mile away is going to be much weaker than your particular transmitted signal. So if it was not sent out in pulses, then the returning echo would not be able to be fitted in between. It is done in such a way that the returning echo comes in between these transmitted pulses back to your scanner and down and then down into the main electronics unit, so that can be displayed as a target on the screen. So this was the first thing. Nautical radar sends out in pulses, whereas this does not. We will see how this system is going to. Initially, as I said, when they first started out, it was started out in the same way by pulses. It had a magnetron. It had everything very, very similar to the nautical radar system. The second thing is, since this has to detect a signal or a target that is quite far away from the ship, the strength of the signal transmitted is in terms of kilowatts. What is the distance over here? I said about 40 meters. Maybe a little more. Let's even go up to 60 or 70 meters. This is a very tiny distance. So if you're going to have the same power, then that power is going to be rebounding off everywhere, and then it's going to be causing havoc with whatever the signal is going to be received back. Okay, so the power of this is in terms of milliwatts. Milliwatts compared to kilowatts of transmission. So second difference is power, transmitted power. Okay, the transmitted power of this is very, very less as compared to your nautical radar system. Okay, so these are the two main differences with regard to your nautical radar system and your tank radar system. Now, as I said, initially they used to follow this particular system even for your tank radar system. And when it was sent out in pulses, they found that, you were getting, and the power was much, of course, it was still much less than your kilowatt power of your nautical radar system. But they found that, they were getting returning echoes from maybe the ladders which are there. It's not just a plain tank. People have to go in and clean the tank. So there were certain ladders and certain pipes. Your pipe with regard to your alarm system, high level. Okay. So all those things, it was rebounding of that, and you were getting spurious returning echoes, and therefore your level was coming very inaccurate. So over a period of time, they changed this thing. That's why we had this initial formula. D is equal to T multiplied by SO divided by 2. It was following the very same thing over here. D is the distance. Here, the D is going to be the ullage. Ullage meaning the space between the level within the tank occupied by the liquid and your particular fixed height to which your level where you're going to be filling up that particular thing. So once you know the ullage, of course, you will know what is the quantity of the liquid within the tank. Okay. So they started off with that very same formula where D was the ullage or the distance. T is the time taken for the signal to go hit the particular target and come back. Likewise here, it's going, hitting the target being the level in the tank and then coming back. So T divided by 2, T coming down and T going up. And SO is the speed at which this RF energy is going to be sent out. RF energy was being sent out over here. Initially, here also the RF energy was sent out. It is still RF energy. Okay. So SO being the speed of light. Speed of light is 1,62,000 miles per second. Okay, 62,000 nautical miles per second. We are considering that for your nautical radar because everything is in knots and nautical miles. We don't talk about kilometers or the ship has traveled so many kilometers. No, they say the ship has traveled so many nautical miles. So that's why even here also they are taking the particular radar, your radar RF energy traveling at the speed of light, which is 1,62,000 nautical miles per second. If it is in kilometers, then it is 300,000 or 3 lakh kilometers per second. Okay. And miles, I forget what it is in miles, but Americans use miles. So they'll be more concerned with that particular thing. Over here, that same thing is going to be transmitted, but they will be using this particular one because we are talking about meters. We are talking about meters, not kilometers. Okay, so everything was being used as in your nautical radar system much, much earlier. But when they found that certain errors crept in with regard to the level, they had done more R&D, research and development. And then they came out with another system, and that system of measurement is called the FMCW, frequency modulated continuous wave. So that is the third difference over here. You were having pulses in your nautical thing, but here in your tank level radar system, your particular radar signal is being transmitted continuously and not in pulses now. Earlier, yes, it used to be in pulses, and they found that we are getting errors. Now it is being sent out as a continuous radar system. What happens to the echo? Echo would get swamped, no, if it is going to be continuous, whether it is a low thing or less traveling distance as compared to this. If this is going to be continuous, then the echo is going to be affected, isn't it? But this FMCW is slightly different. It is not depending on the echo returning, it is depending on the frequency. That is why it's called frequency modulated continuous wave. Now, how does this frequency modulated continuous wave work? Right? So here's this transmitted signal, and they are showing it in a graphical situation over here over a period of time, and this is what is going to be the frequency. When the radar transmitted signal is going to be sent out at a particular level within the tank, the frequency, say at this particular thing, the frequency is going to be that much. Now, as this particular radar signal is traveling, and then it hits this particular thing, it is traveling, and then it is hit that particular level within the tank. And as you can see, the frequency was one thing over here, and the frequency is another thing over here. The transmitted signal is changing its frequency depending on where it is hitting. Suppose the level of the tank had reached over here, must be over here. Okay, so the level, the frequency at that particular point, say this point, the frequency of the transmitted signal would be here. So as you can see, as the level is going to be increasing, the transmitted signal frequency will be varying. So if the transmitted signal is varying, it's going to have an echo returning. This is your echo returning. Similar to your transmitted signal frequency varying, the returning echo signal also had a frequency difference. So if the frequency of the transmitted signal at that particular point was there, the received signal frequency was at this particular thing. But this particular frequency of the received signal is different from the transmitted signal at that same point. Okay. Likewise, if over here, the transmitted signal frequency was one thing over here, the received signal frequency is slightly different from that. as you can see over here. This is the transmitted signal. This is the thing. You can't make it out very clearly, but let me indicate it by a different color. Okay, so here's your received signal, and your received signal, if you're going to be thinking, it is going to be not spot on over here. Slight difference is going to be there. And this is that slight difference that is going to be there between your transmitted signal and the reflected signal. This difference frequency FR is directly proportional to the level within the tank. The difference frequency is directly proportional to the level within the particular tank. So this is how today your particular system is going to be working. Your FMCW, as I said, SAB was the one that discovered this. They held on to the patent for quite some time, and now all the other manufacturers, that patent is not going to be forever. It is only for a limited amount of time because they discovered it. They needed to make the money from their discovery. So that patent was whatever for how many years, I'm not sure, but then they made hand over fist money. And then when the patent expired, then all the rest jumped on and grabbed onto this particular thing because, yes, it was giving them very, very accurate reading. So this is what is the thing that is being used today. Okay, your FMCW is going to be transmitting a continuous wave, and the different signal, which is this, that is going to be received by this particular dish antenna, which is then going to be sending it to your TG, your electronics unit. That is going to be sending it to your SCU, and you will be getting your display on your main display and backup display, whether it is there on your bridge or on the captain's cabin. You will be getting the display of that particular level in the tank. Okay, everybody clear with regard to your tank radar level system? Any queries or doubts? Okay, somebody is asked capacitance and radar type level gauge, what type of problem occurred and how? As I said, your capacitance type is never used on board the ship. Never have you ever found, you go on any tanker, you will never find the capacitance thing for a very simple reason I gave, is that you're not loading the same cargo again and again. Unless you're loading the very same cargo again and again, then only you're going to have the capacitance type. Now, with regard to your tank radar system, yes, you can have several problems. And one of the problems is this dish antenna. This is one of the main problems, okay? Of course, if your electronics unit and all that is going to go kaput, then it is going to, you're not going to get a reading. But one of the simple problems is related to this dish antenna. Okay, even going to your normal direct to home TV, yes, you've been receiving good signals, etc. And then comes one bird and decides in that Allen B, he is going to build his nest. That's the time you get problems with your direct to home TV. Okay. In the case of this particular dish antenna that is going to be there within the tank, okay, and let's switch to this particular thing and go back to that particular diagram. Okay. Sorry. Right, you can see it, it is within that tank, okay, and that is over here. This is all forming part of the internal part of the tank, isn't it? So obviously, whenever you're going to be loading cargo and whatever the thing, you will have fumes, no, of that cargo. So that fumes of the cargo can get deposited on the particular dish antenna. It can get deposited on the LNB. Here they're calling it the antenna feeder, one and the same thing. So if this gets contaminated, your signal is going to be retarded. Even if it is that FMCW type, your signal is going to get retarded and you will be getting problems. Sometimes you will have an error saying that level signal lost or something to that effect. Okay, it depends. Now, how do you solve that particular problem? That problem is solved or can be solved only when you are going to depressurize the tank. Remember, we said we had the IG pressure sensor. So the IG pressure in the tank will have to be released. So your tank should not be pressurized. First and foremost, the chief officer will make certain that, adequate precautions are going to be taken, etc., etc. And then he will depressurize, in other words, release the IG pressure within the tank. Then what you do is come to the particular unit, not the TGU, but on this unit, you have a small opening. Make certain that the tank has been depressurized and then only try to open this opening. When you open this opening, you will see directly, if you're going to bend and look through this, you will see your dish antenna followed just a little below by this antenna feeder. Use a soft, clean cotton rag. I'm going to say the word cotton rag within inverted commas. Why am I using cotton rag? Can anybody tell me? Yes, anybody can tell me why I'm using a cotton rag and not any other rag? What about tanker safeties? You all must have done safeties, no? Tanker safeties, one of the things that is very pertinent, and I had mentioned in passing with regard to when we did that chapter, that when you go out from your A deck, generally the exit and entry point, whenever you're loading or discharging in port, is from the A deck. Let it be port side, let it be starboard side. Okay. As I said, there is a small space in between your main accommodation and the outer door. And in that small space, you have a figure of a palm where you have to place your palm there and then exit to the outside. That is to discharge any electrostatic energy. So if you're going to use any other cloth other than cotton to clean this, that particular cloth can develop electrostatic energy. And remember, we have depressurized. We are not having any more IG inside here. So when you're removing the IG and depressurizing the tank, if you're going to use any other cloth other than your cotton cloth, you are risking a huge fire and explosion. Remember, a small spark will be enough to create a fire and explosion. Okay? Everybody clear? So this is that particular thing. Okay? So I hope the doubt has been cleared by that person. Okay? Any other queries or doubts you may have on your tank radar system before we move on to the final sensors, and that is your fire detection sensors. Just give me a short a minute. Okay, so let us now move on to the last of the topics, and that is your fire detection sensors. Okay. Okay, so talking about your smoke detectors are of two types generally. Number one, the ionization type, and number two, the photoelectric type. Now, the photoelectric type is very similar to a proximity sensor. And we had spoken about the proximity sensors in the form of inductive, capacitive, and photoelectric type of proximity sensors, apart from the sound type. Okay. So the photoelectric proximity sensor, we said, works on the principle of beam on, beam off. So this type of smoke detector will be working on that same principle, beam on, beam off principle. Okay, so you can also call it a proximity sensor if it is a photoelectric type. And we'll come to the photoelectric type a little later. Same way as your proximity sensor, the photoelectric type work, that particular thing, if it is a smoke sensor, is going to work on a similar manner. But generally, questions are asked on the ionization type. And whenever you go on board, you will find generally this type of smoke detectors rather than your photoelectric. Of course, depending on which is the company, how much they're going to be costing. Of course, this one is going to be more expensive than the photoelectric type. But the photoelectric type is generally not used for the simple reason is that your light receiving detector, once it gets dirty, you are going to have innumerable problems. Yes, you might clean it. Now, if you're on a ship that has over 300 sensors, I'm pretty certain nobody is going to be doing that cleaning job. You'll be using your entire time only cleaning those sensors. So therefore, it makes it an impractical thing. But yes, it is still used. In fact, I had a student in 2019. He was working on board a passenger vessel, an Italian passenger vessel. And they did have ionization type. But from ionization, they changed to the photoelectric type for the simple reason, in the ionization type, they are using a radioactive material. So as you know, passengers, they sue a company for any and everything. If they ever came to know that there was radioactive material material in their own cabin in the form of a ionization type of detector, they would sue that company. And as you know, when you sue 99%, 99.9%, you can say, of the times, the particular thing goes for the passenger. So whilst they make their money, the passenger vessel can get back, the passenger company can go bankrupt. So they had changed from the ionization to the photoelectric type. And he was telling me that they use special gowns, they use special gloves, and they disposed of it in the proper way that anybody would be disposing radioactive material. So such was the this thing on that ship. Okay, but as far as I know, there have been no detrimental effects to anyone who has been sailing on this. Okay, so let's see how this type of ionization smoke detector works. Then we'll come to the photoelectric. So as you can see here from this photograph, There are two chambers. One is an open chamber. You can see these slots. So that means whatever outside air is there can get inside this particular sense. The other chamber is a sealed chamber. That means nothing from outside can get inside. Now, these two sealed chambers have that particular radioactive material. That radioactive material is called americium-241. Okay, the radioactive material that we are talking about is called americium-241. Now, what does this radioactive material do? Any radioactive material, whether it is supplied energy or not, that radioactive material will be always emitting electrons and protons. Protons being positive and electrons being negative in nature. Okay, so they will be always emitting that particular energy. Now, these two chambers and the circuitry is simplified here in this circuit diagram. Why are we taking this circuit diagram? Because it has been asked several times, not only in your writtens, but in the orals. How does your ionization type of detector work? So you can draw and think or keep this in your head, whichever is easier for you. But I would suggest that you draw it. It's very simple to draw. Draw a transistor, and remember a transistor is biased by two resistors. Instead of the resistors, put these two chambers. So these chambers are going to be acting like a bias for this transistor. The transistor that is being used over here is going to be acting as an open and closed switch, not for amplification. There is a relay, but this relay is a current operated relay, not a voltage. That is why it's coming in series. Okay, so it is a current operated relay. And of course, excuse me, you're going to be having your sorry, you're going to be having your alarm circuit and of course your power supply for your circuit. Okay, so now let's see how this thing is going to work. The ionization type of smoke detector. One is the sealed chamber, and the sealed chamber is shown here at the top, and the open chamber is shown here at the bottom. This thing that I've shown with arrows is your americium-241 that is emitting those protons and electrons. In other words, it is radiating. Now, when there is no smoke, this americium-241 is going to be emitting those positive and negative charges. Here also in the sealed chamber, the same thing is happening. So let's see from this thing over here. We are now talking about this particular, whether it is the open or sealed chamber under normal conditions. Okay, you are having the positive charges, you are having the negative charges just going around aimlessly being emitted by this americium-241. Now they will just keep floating around till a positive and negative thing is connected to two plates. If this battery was not connected, then it will just keep floating around here and escaping even to the outside because there is no particular direction they are going to flow. But with these two plates, and you connect a battery, a positive and negative, positive to one plate, negative to the other plate, then these are going to be attracted. The positive obviously are going to be attracted to the negative plate. The negative is obviously going to be attracted to the positive plate, and a current is going to be flowing between the two plates. So when you're going to be in the normal condition, okay, when the battery is supplied, so when you're having the power supply, current is going to be flowing from the positive through the current operated relay. Remember, both are now going to be conducting. Okay, so you are going to have a current flow through the sealed one, through the open chamber, back to the negative. Okay. This is the normal condition. The nominal current flow shown in the blue arrows. This nominal current under normal conditions is not enough to activate this current operated relay. So the relay doesn't get activated. When the relay doesn't get activated, obviously it's not going to close the circuit to give the alarm to the outgoing alarm for detection of smoke. Normal condition. What happens now when you're going to be having a fire? There is no smoke without fire and vice versa. So when you're going to have a fire, there will be smoke. Smoke is not going to enter into this chamber, but this being sealed, no smoke is going to enter over here. So when smoke enters into the open chamber, it is going to enter here into this chamber, not into this chamber. And let us see what happens when it enters into the lower chamber. Okay, so now we are talking about a condition when smoke enters. Smoke is entering into the lower chamber, not the sealed chamber. And when smoke enters into that lower chamber, the smoke that is depicted here as black dots, they start clinging on to the positive and negative charges. And when they start clinging on, they negate the charges. Now we know that this purple thing over here was a negative charge because they have colored it as thing. But really speaking, you will not know which is a positive, which is a negative charge. Just because they have colored it over here the same way, you knew that this was initially a positive charge, but now since smoke has come and latched onto it, it has lost its positive charge. Likewise here, smoke is latched onto this thing, it has lost its negative charge. And then no matter if you're going to be supplying that power supply to the positive plate and the negative plate, these are not going to go anywhere because they don't have any charges. So there's not going to be any more current flow between your positive and negative plates. So when you're not going to have any current flow in your open chamber, so let us now cancel out this thing. No more current is going to be flowing here. The current, where will it flow now? It's going to flow through this relay, through the sealed chamber, because the sealed chamber is unaffected. It's going to be exactly like this. Okay, the current is still going to flow through the sealed chamber. And now it is going to be taking a different route rather than going this way. Now this one is blocked. The current now goes into the base of this transistor and back to the source. So everybody knows from the very basics that your transistor is a current operated device. So when a current is going to be flowing into this base, the transistor gets forward biased. When the transistor gets forward biased, what is happening? It is nothing but a switch that is being closed. Okay? The switch which was open, in other words, when the transistor was not conducting, the switch was open circuited. Now that the transistor is got forward bias, it is like the switch now that is being closed. When a switch is closed, it is forming a direct short circuit right through. So where's the current going to flow? Instead of flowing now like this, the current is going to be flowing in a very, very high manner. Okay, and that is why I've drawn these particular red arrows. Let's make it even thicker. Okay, the red arrows are now going to be indicative of a much higher current flowing in this manner. Remember, a short circuit current where we had spoken about in various other things, it is 1,000 times the FLC. So obviously here also the current that is going to flow because of this short circuit, the closing of the operation of this particular transistor, the activation of this transistor is acting like a short circuit. A very high current is now going to be flowing. That current obviously is going to be flowing through this current operated relay. So since a large current is flowing through this relay is going to get activated. When that relay gets activated, it is going to close the switch. which is the supply to your alarm circuit, and your alarm will be issued. Okay, so this is how your ionization type of smoke detector works. Any queries or doubts on the operation of this ionization type of detector? Okay, so we'll see a short video on this ionization type of smoke detector. Okay, so here they're showing the photoelectric. They will show the ionization. So, okay, let's see the photoelectric thing. And we'll see the notes on that and how it works. And then we'll come to the video, okay? Right, we'll see the photoelectric one, how it operates, and then we'll come to the video where both are being shown, okay? Right, so coming to the photoelectric type, when we are done the photoelectric proximity sensors, we spoke about the OMD, where you had the direct and the indirect type. So here also in the photoelectric type of smoke detector, you have the direct as well as the indirect type. Okay, so this is the indirect type and this is your direct type. And here the direct type is very similar to that of your oil mist detector. Okay. In the direct type, you are having your light source, and at the opposite end, you are having your light detector. So light is going to be flowing when there is no smoke. Light is going to be flowing, okay, directly onto the detector, and your detector is going to be conducting. Okay, so there's going to be a nominal current flow. So your nominal current flow, let me change the color of the pen. Okay, so this is your normal current flow, which is a logic 1. And only when it is going to get blocked by smoke, there's not going to be any current flow. Okay, so from a logic 1, you are going to go to a logic 0. So this is your direct type of thing. Whenever there's light falling on the detector, a nominal current flow is going to go to your alarm circuit, which is basically a logic 1 signal. And the moment smoke comes due to a fire, your light is not going to go through your smoke over there. Nothing is going to be falling on the detector. This current flow is interrupted, and therefore from a logic 1 is going to go to a logic 0. That is the signal for triggering of the alarm circuit. Okay. What about the indirect type? Okay, so you can see the indirect type. Remember, as I said, when there is no smoke, then you're going to have the light that is going to be going directly across. Okay, directly across. There is no light detector over here, but where is the light detector? The light detector is at 90 degrees away. Earlier, in the direct type, the light detector was here, in which case the light would have fallen on the light detector. But now in this case, since it is at 90 degrees away, no light is falling. So where in the direct case you had a logic 1, because there was a nominal current flow, here there's no light falling on your particular light detector, and therefore you're starting with a logic 0. Okay. Now, when you're going to have a fire, the smoke is going to enter into this chamber. When smoke enters into a chamber, then that particular smoke is going to be blocking the light transmission. Earlier it was going straight through. Now it is blocking the transmission of light going right through and through. On the contrary, it is going to get reflected and is going to be reflected in the downward direction. Because there is no other opening, it is going to be in the downward direction. And now that light is falling on this light detector, and now you are going to get a current flow. Okay, so that current flow is to the alarm triggering circuit, where initially here it was a logic 0. Now you're going to get a logic 1. Okay, and when you're going to get a logic 1, then that is going to be a alarm, triggering alarm for your smoke detector of the indirect type. Okay, everybody is clear now with the direct and indirect type of smoke detector, the photoelectric type of smoke detector. Any queries or doubts, gentlemen? Okay, now let us check out the video. Okay. Sorry.
Welcome back. In this video, I'm going to explain how smoke detectors work. There's two basic types of smoke detectors. There's a photoelectric and an ionization. And first we're going to look at the photoelectric. So the principle is easy enough. There's two basic parts to the chamber of a photoelectric smoke detector, and that's the light source and a photocell. And the way these are set up, the light source is not lined up with the photocell. In other words, if you were to draw, the path of light from this light source, it's not hitting the photocell. The way that these are put into alarm, or the way they detect smoke, I guess I should say.
Okay, so this is the indirect one. So you already know what is an indirect type. If it is a direct type, then this photocell would have been here. Okay.
Is when smoke enters the chamber. I'm going to simulate smoke here. Let's say this is smoke. The light refracts off the smoke particles. So now the light will, it'll go every direction. It'll scatter, but some of it will hit this photocell. When the photocell sees light, it produces a current, and the circuitry inside the photoelectric smoke detector interprets that current and puts the device into alarm. So if we were to then go and wire this to our fire alarm panel, it would look something, well, it would be powered up the same way these have been all along. This is just a 2-wire smoke detector, I should point out. There are also 4-wire smoke detectors, which the wiring's a little bit different, and I'll explain that in the future. But this isn't going to, once this goes into alarm, it's not going to exactly short out these terminals like a pull station would. It's not a dead short, but it does increase the current significantly, and the fire alarm panel interprets that as an alarm, and the horns go off, etc. All the things we've discussed up to this point. But the thing I want you to focus on is how the device detects smoke. So there's a light source. It's not quite lined up with the photocell. Once smoke enters the chamber, the light refracts off of the smoke, and some of it hits the photocell, and then the device goes into alarm. There's another way to draw this, which I think might make it even a little bit more clear, even though the one that I tried to draw initially looks a little more like the devices I'm used to seeing. But if you look at this, you'll see it sometimes when you look this up. It'll be drawn like a T shape. So you got your light source at the top, and this is your light source, and it's going on the top of this T, and your photocell is down at the bottom. And once you get smoke into the chamber, same principle. You spray some smoke, and now the light some of that will refract down to the photocell. It'll go into alarm, etc. I think that's easy enough, and I don't want to spend a ton of time on this because there's a lot of information on the internet. You could do a simple internet search and get plenty of explanation of how these devices work. So we're going to move on to the other type, which is a little bit more difficult to explain, a little more difficult to understand. That's the ionization smoke detector. The way these work is there's a radioactive element in all of these ionization smoke detectors, and that is americium-241. And what that element does is it ionizes the air in the chamber, hence the name ionization smoke detector. And bear with me, I'm going to try to explain what that means. So first of all, let's power this up. Same panel, same 24 volts going to our smoke detector, nothing fancy. And that's going to take that power source, or if this were a smoke detector in your house that were only tied to a battery, it would use a battery as a power source. But for right now, I mean, we're dealing with conventional systems, commercial systems, so let's take our 24 volts and go to these two metallic discs. So this is now a positively charged disc, and this one on the bottom is a negatively charged disc because we tied it to our power source. And on the right here is a reference chamber, which I'll explain in a minute. For right now, let's just focus on the left. So there are two oppositely charged plates with nothing in between them right now, just air. You can imagine if we had put a light bulb or something on here that it would produce power because current could flow between positive and negative, but with just air in the middle, no current can flow. Except when they put this americium here, what this does is it changes the oxygen, and I guess to a lesser extent the nitrogen that's in the air, and I'll explain that. We haven't really gotten into how current flows on the atomic level yet, but current flows through conductors and not insulators, and conductors have a free electron. So an electron is a negatively charged particle, and what this americium does to the oxygen and nitrogen particles is it actually knocks an electron off of them. And so then the electron, which is a positively charged element, is a negatively charged element, is attracted to the positive charge. So the electrons, which are now free, are flowing towards the positive plate. And now the oxygen and the nitrogen have a negative charge. They have a positive charge because they lost that negatively charged electron. So now they are ionized, hence the name, like I said, ionization, and they are attracted to the negative plate. So before, the oxygen and nitrogen were neutral. Now they are positively charged and they are flowing towards the negative plate. Their newly freed electrons are negatively charged and flowing to the positive side. I know that's a little bit confusing, but you don't really have to understand that. I want to present it that way, but you don't really have to understand that to understand how these things work. The other thing I want to mention is that this radioactive particle has a half-life. I forget what, I looked it up. I want to say it was like 480 years or something like that. So it's not like this is going to work for a year and then run out of power like, maybe like a battery would. So this is going to continuously happen. And what happens is if smoke gets into the chamber, it bonds to the oxygen and the nitrogen, preventing that current from flowing. So in a way, it's almost the opposite of what happens in the photoelectric. Is once current starts flowing through that little cell, the circuitry interprets that as an alarm. In this one, current's always flowing between these plates, and when it stops, that's when the alarm is detected. Now, you see this thing on the right here. That's what's called the reference chamber. That's in most of these the newer ionization detectors. So let's just draw our power over here, and this would be on a very small portion of the smoke detector. I'm drawing it spaced out so it's easy to see what's going on. But this reference chamber is sealed. It basically does not prevent any smoke to get into this chamber. So these two things on the right and left are identical, except that the one in this orange box does not allow smoke in. And the reason they do that is they monitor both of these things. They monitor the current in both of these, the one on the right and the reference chamber. The one on the left and the reference chamber on the right. And the reason for that is things like air pressure and to some extent humidity can affect the current flow. So you imagine a little ammeter in this circuit so that it's actually monitoring how much current is flowing on both of them. And if current stops flowing on on one versus the other, let's say current stops on this one on the left, but it's continuing to flow on the reference chamber, well, it knows that there must be smoke because smoke's not getting in here, smoke is getting in here, and that's what's setting it off. One of the advantages of ionization smoke detectors is that it's not affected by dust because dust doesn't bind to those oxygen and nitrogen particles. So therefore, you don't have to clean them, and I think they're less prone to false alarms. other than that, it works basically the same way. There is some difference on how they say that, I hope I get this right, they say that the ionization smoke detectors are better at the earlier stages of detecting the earlier stages of smoke, I believe. More like just I want to say like the smoldering of the smoke, whereas the photoelectric are better when there's thicker smoke, heavier smoke. But there's, like I said, same with the photoelectric. There's a ton of information on this. You could do a simple Google search and get plenty of information. But this is I think this is a fairly decent explanation of how these work. And I guess that's it for right now. I will see you in the next video.
Okay, so I hope everybody's understood the working of your both photoelectric and your ionization type of smoke detector. Okay, if I had only shown you the video, then you wouldn't have understood how it is going to be working. So ionization, as he said, because of this americium-241, you are having these positive and negative charges because the air inside is getting ionized. And this is the main cause that is causing these positive and negative charges. Without this, you're not going to have any positive or negative charge. Okay, the americium-241. And based on that, when, as he said, when there is smoke, this positive and negative charges disappear and you're not going to have any current flow. So based on that, and this particular diagram, as I said, this is a simplified diagram. Now that you have understood how it works, it'll be very easy for you to understand. Okay, any queries or doubts, gentlemen, before we move on to the flame detector?
Sir, this advantages, can you repeat again for this ionization,
Yeah, so
dust and?
as you heard in the video, the advantage of this type of detector over your photoelectric type of detector, remember, this is always going to be open. Okay, dust is going to come. Dust can settle on this. That means you have to every time clean it up, everything. And then there is a certain stage in the life of this photoelectric type of smoke detector that no matter after how many times you might clean it, that dust can get impregnated into this. And once the thing gets impregnated, then you're going to get all false alarms. Whereas this one will last nearly forever. Okay, so you would see on your photoionization type detectors on board your ship, how often have you changed it? Very rarely, yes. Okay, after a really long time, yes, it might give a thing. But everything is dependent on this. And what did he say in the video? The half-life of this is something like 400 years. So this can keep on emitting those positive and negative charges for 400 years. Okay, there might be some other mechanical defect. So this can, technically speaking, last forever. Okay, you might have some other issues, which yes, that is why we do sometimes replace the smoke detectors of the ionization type. So this is the advantage of your particular ionization type of smoke detector over your the photoelectric. One is the cleaning, and here you don't require to clean. What is there to clean over here? Nothing. Okay, this continuously gives the thing, and only if it detects smoke, it's going to stop conducting, and the alarm is issued. Nothing to clean. This is within that chamber. The chamber cannot be opened. Okay, you cannot open this chamber. This particular chamber that I've crossed out, the open chamber, is not going to, you're not going to be able to open it out. It is connected, and in fact, connected to the PCB. As you can see, the PCB over here, it's connected to the PCB. You can't open out, and then even if you open it out, there is nothing to clean in it. Okay, so this is the advantage of your ionization smoke detector as compared to your photoelectric smoke detector. Okay.
Okay, thank you.
Right. So let us now, just 1 minute. Let us now go on to the flame sensor. Okay. Now, first and foremost, the flame sensor is used in conjunction with your smoke detector to activate what system in your engine room. It is not used in the accommodation, but mainly in the engine room. So what type of system is that? Because this is one of the questions that is asked in the orals. Come on, guys. Most of you all have definitely been on board. Nobody? Out of the 12 guys? Yeah, go ahead, Mr. Dash.
So what was the question, sir?
Yeah, the question was, your flame detector is used in conjunction with a smoke detector to activate what system on board?
Water mist.
Yes.
Water mist, local fire.
Yes, different, it's known by different names. The most common name that it is known by is your hyper mist system. It can be your water mist system or whatever name they want to call it. It depends from manufacturer to manufacturer. This system makes very fine molecules of water. It is more like a very, 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 very fine spray. And what does this spray do? It smothers the fire by preventing, remember the fire triangle, isn't it? Fire triangle, you require heat, you require oxygen, and you require the fuel. So this particular system is creating a blanket, and by creating a blanket, like just like we are having the foam system deprives the particular thing of oxygen. So you're taking away that part of the triangle. So your hyper mist system is doing that. So please make certain that it is always one smoke, one flame that will be activating this hyper mist system. I had one Charlie some time ago saying no, only on the flame on his ship, only with the flame detector, the hyper mist system activated. So that means something was wrong somewhere. Okay, so probably he didn't this thing, but please do not make this mistake. It is always in conjunction, the flame detector, if it detects a flame, then a smoke detector also has to be activated in order for your hyper mist system to work. Now your hyper mist system is located where in the engine room? Where are the points of location? Yes, you will have the main system somewhere in your steering gear flat, but where are the points at which it is going to be dispersed?
Above the boiler, generator, the main engine, purifier room, incinerator.
Yes, okay. So your 3 generators, okay, even if you're having a turbo generator, there is a thing over there also, but some of the particular ships don't have it because that turbo generator is nothing, is using no oil. It is using steam to generate power. So generally you will not find, on one of my ships I had one. So it all depends, okay. You'll have it at your generators, you'll have it at your main engine, you'll have it at your boiler. If you're having 2 boilers, especially on board tankers, you may have 2 boilers, you may have 1 boiler. If you're having 2 boilers, then on top of both the boilers, okay, when you're saying top of the boilers, not right at the top, but wherever your flame is being admitted into the boiler, your main burner section, okay. You will have it at your purifier rooms. In the purifier room, where? Above which purifier?
Fuel oil purifier.
Exactly. Your fuel oil purifier, not your lube oil. Your fuel oil purifier, for the simple reason is that fuel is heated up. Okay, your lube oil is not generally heated up when it is being purified. So your fuel oil purifier, you'll be having a hypermist dispenser over there. And sometimes on some ships that are having IGG, inert gas generator. Now on your normal tankers, you have your IG taken from your boiler. But on some ships, especially product carriers and your chemical tankers, you will have an IGG system, an inert gas generating system. It is like a mini boiler, but doing the same job. It is generating IG. But there you're using a much cleaner fuel rather than in your boiler where you're using heavy fuel. In your IGG, you're using HSD, high-speed diesel, which is a much cleaner fuel, and therefore you're getting much cleaner IG. Okay, you have the scrubber, everything inbuilt into that system. And since it is using oil to fire that particular mini boiler, so to speak, above that system also, you'll be having this dispensing for your hypermist. Okay, so very quickly, your flame detector. Okay, you would have seen your flame detector, that plastic cover. That plastic cover has an opening that is covered by a perspex sheet. It's a see-through sheet that allows the flame to pass through into a filter. Now, what type of filter is this? It is not a dust filter. This filter is a band pass filter. Now, when we are talking about a band pass filter, we have seen that we are having IR flame detectors. We have seen that we are having UV type flame detectors, and some flame detectors, especially if that particular flame detector is located at the ceiling of your engine room above the main engine, then they will be having UV and IR flame detector combined. Now, when you're talking about UV and IR, they are talking about the flickering frequency of that flame. The flickering frequency of an IR flame is in this region. Okay, IR, you cannot detect. Infrared thing, your eye cannot detect. What your eye sees when there is a flame is in this region. You sometimes see in orange, definitely you've seen yellow. Sometimes you see green, definitely you've seen some blue flames also. So this is the visible thing to your naked eye, to the human eye. But beyond less than this frequency, that is between 4 to nearly 25 hertz, your human eye cannot detect. From 25 hertz and greater, which comes under the UV region, your eye cannot detect. Who can detect it? Is these detectors that are either UV, IR, or a combination of both. So that is your filter over here. So it is a band pass filter allowing those particular frequencies to pass. Goes through a lens, that lens converges it onto a photoelectric cell. This photoelectric cell would give a signal out. Okay, it would give a signal out to the amplifier. And if it gives the signal out to the amplifier would amplify the signal and send to your alarm triggering circuit. But here we have a timer. What is this timer meant for? This timer, maybe whatever it is, maybe 10 seconds or whatever. Until this timer counts down, this signal is prevented from going through. So only when the timer is counted down, then the signal is sent through. So this timer is acting as a prevention of creating a false signal from triggering the alarm. Until and unless the timer counts down, no signal is going to be passed through. So let's say you had one, short this thing. So yes, it has been detected over here. The timer starts. But meantime, the flame has gone. timer is counted down, meantime that signal is gone also from here. So nothing is going to be passed through. So your timer is used over here to prevent any false signals from triggering the alarm for that flame detector. Okay. Everybody clear with your flame detector and how it works? It's a very, very simple explanation for this. Okay. Right, gentlemen. So we'll call it a halt for today's class. Tomorrow we are left with the heat detectors. It'll take some time for explanation. We will definitely finish off with the heat detectors and then shift on to a new topic. Okay. So this will take some time to explain. So I will not attempt to do it now. Otherwise, it will take another hour or even more than that. Okay. So tomorrow we'll be doing the heat detectors, and then let's see what is the topic after that. Converters, that is synchro converters, cyclo converters, and because we are doing those converters, shaft generator, which is using one of those converters. Okay. So that's it, gentlemen. Thank you very much for joining today. And I will see you again tomorrow morning at 11 o'clock.
Thank you.
Welcome.
Thank you, sir.
Thank you, sir.
Welcome.